are going to see the topic that is related to the analysis of proper cantilever beam subjected to a UDL. Coming to the question, determine the reaction components for the proper cantilever beam that is subjected to uniformly distributed load as shown in figure. Draw shear force and bending moment diagram. So this is a question that is given to you. So here AB is a proper cantilever beam. So for this beam, it is subjected to a UDL of W kilonewton per meter and having a span of length L. So before analyzing this problem or before determining the reaction components, first we should find number of unknowns for this proper cantilever beam. So for this, you have to find write how many number of reaction components are there. So first step is write number of reaction components. So for this beam, you can just see that here A is a fixed support. So for this fixed support, you are going to have three reactions. So one is horizontal, another is vertical, and another is moment. Therefore, HA, RA, and MA. And coming to this B support, it is a proper one. So which is like a roller support. So it is having only a one reaction, that is a vertical reaction. So which is RB. So total number of reactions are 4. So that is HA, RA, MA and RB. So now coming to the next one, we have number of static equilibrium equations are 3. So for two-dimensional, there are 3 equations are there. That is sigma fx0, sigma fi is 0 and summation of moment in the xy plane will be equal to 0. So you're having degree of static indeterminacy will be equal to number of reactions minus number of static equilibrium conditions. So that is 4 minus 3, it is 1. Now by balancing the forces and by using this equations of static equilibrium conditions, we know that sigma fx equal to 0. And here there is only a vertical loading in this problem. Therefore, HA is only the horizontal component. So that will be equal to 0. Another equation is there, that is sigma Fy equal to 0. So that is summation of your vertical forces will be equal to 0. So here the vertical forces are RA and RB in upward direction. Whereas the downward, the total load on this beam is W kilonewton per meter, that is UDL. Therefore, the total load will be equal to W into L. So therefore, RA plus RB will be equal to W into L. So this is a equation we are getting. Next, as we know that this proper cantilever beam is indeterminate to 1. So we can't solve this problem. So by using the principle of superposition, what I'm going to do is I'm going to make this entire proper cantilever beam divided into 2 parts. So first part will be a simple cantilever beam with a UDL, and the second part will be a cantilever beam with a point load at the end, that is your at the end B. So now you can see that this is a first part, that is a cantilever beam with the UDL, external load only, and this plus you're having another beam which is having, this is also a cantilever beam at B, and you're having a vertical reaction, that is your RB. So by adding these two figures, we can get the above proper cantilever beam. So here I am treating the RB reaction to be a redundant force. So that is your vertical reaction. Next, coming to our next step, we are going to calculate the reactions. So for this, as we already know that this is a proper cantilever beam which is having the reactions of RA, RB and MA. So for this, what I am going to do is I am going to balance the deflection at this point. How I am going to balance the deflection at this point is, so as we are making this entire proper cantilever beam into 2 parts. That is, one is cantilever beam with UDL and another one is your cantilever beam with your vertical reaction. So what I'm going to do is, so for this cantilever beam, with the UDL. So we are going to have a deflection of downward. So that deflection, and due to this vertical redundant force, you are going to have an upward deflection. So the net deflection at this B point will be equal to 0, as we don't have any settlement condition and all. So as we are considering the prop to be a rigid prop. So that is the reason we am writing here that balancing the deflection at end point, as net deflection at the end will be equal to 0. So this condition we can call it as a consistency condition also. So due to this given uniformly distributed load, the deflection at this B will be given by, so you can see this is a deflection 1 due to this external load acting. So the deflection is given by WL power 4 by ATI. So this one we are deriving in the deflection of beams concept, which has been dealt in the previous courses like strength of materials and all. So here I am directly using the formula for a cantilever beam, which is having a UDL. So the deflection formula will be WL power 4 by ATI. And next one, this is your deflection one. So this deflection is your downward deflection. Next, coming to your second case, that is the upward deflection of a cantilever beam. So this is a cantilever beam which is having a prop here. So due to this prop condition, due to this vertical reaction at B, so we are going to have the deflection in upward direction. So the deflection here, the formula is RB into L cube by 3EI. So due to this point load acting vertically upward, so we are having WL cube by 3A. So here the load is nothing but your reaction in upward direction. So that is your RB. So delta is RB into L cube by 3EI. So that is the deflection I am writing. So this deflection is in upward direction. So from consistency condition, we can say that the net deflection at this B point will be equal to 0. So that means upward deflection will be equal to downward deflection. Therefore, by equating these two terms, we are going to get RB will be equal to 3WL by 8. So as we already know that RA plus RB is equal to the total load, that is W into L. So from this expression, if we calculate RA, you are going to get it as 5WL by 8. So this is how we are going to calculate the reactions. Next slide. So in this, we are going to calculate the moment. So same the beam we are considering RA, RB and moment. So now RA we know 5WL by 8 from previous part. RB also 3WL by 8. Now we are taking moment about this B point to be 0. So we can write RA into L, so which is in the clockwise direction. So plus I am considering, minus MA, so which is in anti-clockwise direction, and minus W into L is the total load into L by 2 about this point. So that is the equation we are writing. So everything is equating it to 0. Therefore, MA will be equal to, by solving this equation, we are going to have MA will be equal to WL square by 8. So as we are getting MA value as positive, so whatever the sign convention we are assuming here, that is in hogging in nature. So this will be the same direction only. For suppose if you are getting MA to be a negative value, so then this sign convention will be in the opposite direction. So that will be like this. So as we got it in the positive direction, so the sign convention will be in this direction only. So that is anti-clockwise. In the next, coming to the next slide, so we are going to draw the shear force diagram. So for drawing the shear force diagram, so just we will take a beam that is there already given to us. So this is of span L and this is AB supports, and we know the reactions. RA is 5WL by 8 and RB is 3WL by 8, and this is a moment that is WL square by 8. So this calculation of reactions and the moments have been taken place in the previous slides. So after getting this all, we have to take a section and we have to solve, we have to write the shear force equations. Now, when we take a shear force at a section XX, So I am taking a shear force section XX at a distance of X from the support B. So here I am considering the origin as B. So therefore X is equal to 0 at B and X is equal to L at A. Now, before writing the shear force equation at XX section, so let us first recall the sign conventions for the shear force diagram. So coming to the shear force sign convention, when we take an element here at any section of a beam, so this is an element I am taking. So when you cut a section to this element, towards your left hand side if the arrow is upward, and towards your right hand side if the arrow is downward. So that means towards the section, if you are having a clockwise shear from either left hand side or either from right hand side, so then the sign convention will be a positive one. So that is your positive shear. Now when we take the same element and when we cut a section, and towards your left hand side and towards your right hand side, about the section, if you are having the shear to be in anti-clockwise direction, you can see here, this is in the anti-clockwise direction. So then the shear we are going to consider it as a negative shear. So this is a sign convention. Now following this, when we write a shear force at a XX section, we can write this 3WL by 8. This vertical reaction is in anti-clockwise direction. Therefore, minus 3WL by 8. And whereas this W, intensity of the load, is in the clockwise direction. Therefore, it is plus W into X. So the limits here we are going to take are X is equal to 0 to L. Why I'm taking for entire 0 to L is, here we are not having any load deviation and all. So therefore, as the load is throughout 0 to L distance, whenever you want to cut at any distance, you are getting the same equation. Therefore, the shear force equation from 0 to L is minus 3WL by 8 plus WX. So it is applicable for 0 to L distance. Now, when we consider X is equal to 0, it is minus 3WL by 8. When we consider it X is equal to L, you are getting a positive value of plus 5WL by 8. So these are the two things we are getting at X is equal to 0 as well as at X is equal to L also. Now, when that means we are changing the shear force from negative to the positive value. Therefore, shear force at X is equal to 0. I mean, we are equating this shear force equation to be 0. Therefore, we are getting the X value to be 3L by 8. So, at X is equal to 3L by 8, we are getting the shear force to be 0. Now, we are going to draw the shear force diagram. So, we will take same AB line. So, at B, you are having a negative value of 3WL by 8. And again, at L, you are having, it is positive value of 5WL by 8. And at X is equal to 3L by 8, you are having the shear force to be 0. So as it is a UDL, it is linearly varying. So this is a final shear force diagram we are getting. So you can shade this portion also. This is how we are going to draw a shear force diagram. Now coming to the next one. You are going to draw the bending moment diagram. So now coming to the bending moment diagram, same, the beam we are going to take a proper cantilever beam. So for this beam, this is a span and these are the supports and these are the reactions as we already got it, RA, RB and MA. So after getting these reaction values writing here, we are going to take a section at this portion, that is XX, which is having a distance X here. So in the previous slide, we have written for the shear force. Now we are going to write the bending moment. So bending moment is nothing but the reaction or a force into a distance, perpendicular distance. So here we are having at this section, we are going to write the bending moment equation. So before writing the bending moment equation, we are going to just see the sign convention. So coming to the, these are the limits, that is X is equal to 0 is at A and X is equal to L is at the, X is equal to 0 at the B support and X is equal to L at the A support. So from B, we are taking the section. So now coming to the sign convention. So when we take a section at this point, any point, so towards the section, if the arrows are heading upward, okay, so one direction can be anti-clockwise, another direction can be clockwise also. But when the arrows are heading upwards, towards upwards to the section, so then the sign convention will be positive. That means towards your left hand side if it is clockwise, and towards the right hand section if it is in the anti-clockwise direction, then this is a sagging moment we'll call. And this sagging moment we can make it as a positive moment also. Now coming to the next one. So when the arrows are heading towards downward towards the section, so that means towards your left hand side if the moment is in anti-clockwise direction, and towards your right hand side of the section if the moment is in the clockwise direction, so then the moment is in the negative value. So that means you can call this moment to be a hogging moment. So sagging moment means positive and hogging moment is a negative moment. So after knowing this sign convention, at this section, when we write a bending moment equation, so you can write here at B reaction, B support, we are having a upward arrow value. So upward arrow in the sense towards the right hand of your section, you are getting it as an anti-clockwise. So even though it is in the anti-clockwise direction, the arrow is heading towards the upward of the section. Therefore, the bending moment equation about this XX will be 3WL by 8 into X minus this one is in the downward, this external load W is in the downward direction. So that is minus W into this distance is your X distance. So W into X is the load into X by 2 will be your distance that is acting, moment is acting towards. So that is Wx into X by 2. So here the limit for this equation will be 0 to L throughout the section. So now we are going to substitute bending moment at X is equal to 0. Here bending moment will be 0. And at X is equal to L when we are substituting, then you are going to simplify the above equation. You are going to get minus WL square by 2. So this is at X is equal to L. So now when we draw a bending moment diagram, so to draw a bending moment diagram, we know at X is equal to 0, it is 0. And at X is equal to L, you are getting a negative value of minus WL square by 2. In the previous slide, we got the shear force to be 0 at X is equal to 3L by 8. So where the shear force is getting 0, there you are going to get maximum moment. Therefore, bending moment maximum will be equal to, you are going to substitute in this BMX equation, X is equal to 3L by 8. So when you substitute this 3L by 8, you are going to get bending moment maximum will be equal to 9WL square by 128. So this is a positive moment again you are getting at X is equal to 3L by 8. So that means your moment is, you are getting a positive moment as well as you are getting a negative moment also. Therefore, there will be a change in the sign convention. Therefore, what we are going to do is, you are going to make this bending moment equation to be equal to 0. So at X is equal to some value, you are getting the bending moment value to be 0. So we are going to find that. So BMX equation, I am equating it to 0. So that means this equation 3WL by 8 into X minus WX square by 2, I am equating it to 0. Therefore, I am getting X is equal to 3L by 4. I am getting the bending moment to be 0. So now by using all these values, I am going to draw the bending moment diagram. So this is an AB beam. So now what I am going to make is at B support, I am having a moment to be 0. At X is equal to L, that is A support, I am having minus WL square by 2. I am getting. So that is the reason I have drawn the bending moment in the downward direction. So this is a negative value. And again at X is equal to 3L by 8, I am having a positive moment. So at the X is equal to 3L by 8, I am having a positive moment of 9 WL square by 128. So this is a positive moment. Again, at x is equal to, at x is equal to 3L by 4, I am having the moment to be 0. So this is x is equal to 3L by 4. So you can just see here. So this is A support and this is a B support. So at x is equal to 3L by 8, I am having a maximum moment. Okay, this is XX section. And at x is equal to 3L by 4, I am having the, so this is an arrow that is continuing. So at x is equal to 3L by 4, I am having the bending moment to be 0. So this is an x distance. This is a bending moment diagram. So we can see here. So this entire, so the at x is equal to L by 3L by 4 from B distance, we are having the bending moment to be equal to 0. So you can shade this bending moment diagram also. So this is how we are going to draw bending moment diagram by using these values. And these are the textbooks and references.